So the last talk of the session is going to be Oliver Tavakoli.
Correct.
Ooh, I didn't think I was going to get that right. Who is the CTO at Vectra right now. He's got a long career in this space. He's been
That's not the slide deck.
No, it should be open.
Okay.
Here, I'll get it. There you go.
There we go.
And both mics should be hot.
Okay.
So prior to Vectra, he's spent time at Juniper, IBM, Fluent, Novell, among other places. Let's welcome Oliver.
Thank you. So I realize I'm chasing this a little bit since we've had a lot of conversations about data science and ML and AI, but I thought, a little bit of a grounding for those of you who aren't deeply literate necessarily in the space. Oftentimes I kind of go to a show like, Gartner or RSA show, and you walk through the floor and it's buzzword bingo. You just see every word thrown out there without even a sense of a relative relationship of these terms to each other. You'd believe by going to some booths that machine learning is basically a precursor to AI, where of course AI has existed for quite a bit longer than machine learning. You hear things about GPUs and TPUs and TensorFlow, and we had a little bit of a conversation earlier about the interpretability of neural nets. So trying to basically understand all of these things and just form them in your brain and have some mental framework by which to actually have conversations with people and kind of probe them with the right questions. That's basically the goal of this prezo. So at the highest level, whether you want to think of this as a classification thing, there is supervised learning. Now, supervised learning, generally speaking, the archetype of this is, as an example, the notion that you can go onto your photo library and you can type in the word cat and every photo with a cat appears. How did somebody create that? They created that by taking a pile of cat photos. How did they know they were cat photos? Well, they didn't quite know they were cat photos, but they pulled them off the internet and they had a caption underneath them and had the word cat associated with them. So it's not a totally pure sample. It's kind of 99.44% pure. Then they take a whole bunch of other pictures that don't have cat on them, and then they try and kind of build a classifier to basically say, what's the likelihood this picture has a cat in it or doesn't. And then once they've trained it up, the beauty of that approach is they can just run that classifier against all the photos in the world. The training occurs once, and then that learning is just applied. Now, they may periodically go back and retrain the algorithm because they have new features that they have come across, features just being a fancy data science name for variables. So they may train a slightly better algorithm. They may decide that this neural network should be 6 layers deep rather than 4 layers deep. It should be 128 nodes wide rather than 72 nodes wide, and it'll just remember things a little bit better. The other technique that you will see out there, oftentimes, again, this is often under the banner of anomaly detection. So you do unsupervised learning. So what does that mean? You just kind of look out in space, think of our own galaxy, think of the universe, and you find in the universe you find galaxies. Oh, these things are clustered close to each other. Within those there are systems with stars around them that are clustered even closer, and so you come up with some notion of closeness and farness, and that doesn't sound terribly complicated, but it is actually quite complicated because I try and kind of give an example to people. Let's say you take a whole bunch of HTTP transactions, right, and you try and compare them in terms of their similarity or dissimilarity, and you decide that one of your variables is, okay, where did this come from? Like, where in the world did this come from? And so let's say, well, how distant is this origin from some other place? One of them was in Kazakhstan, one was in Houston. How many miles is between that? Okay, that could be one variable. The next variable is the user agent. How similar are these user agents? Okay, how do I judge that in numerical terms? Well, there are all sorts of ways of doing that with strings. And the next one is how many bytes are in this thing. Again, that is a delta in byte count. Now, number one, you've got to take those three variables and turn them into numbers. Number two, you've got to somehow combine them, right? It's not like a straight Euclidean three-dimensional distance where these things are all the same units. So there's a lot of art that goes into picking distance functions and judging how far things are from each other. And depending on which distance functions you use, your clusters will come out entirely differently. So this is not as straightforward as simply saying, I apply an algorithm, I choose an algorithm, I apply it to the problem, and presto, I get the same results. The third one, which is not talked about a lot, is reinforcement. So there is a way of building algorithms, which is, playing games. Basically, think of this as, you're trying to train a program on how to get out of a particular maze, and you kind of give it feedback. You tell it warmer, colder, and sometimes it'll have to realize it actually has to go through periods of cold to get warm and to get out of the maze. In other words, you will have to go further away from the exit of the maze in order to actually then come back to that exit of the maze. So you can use reinforcement learning. One of the interesting questions that always kind of comes up in all these approaches, if you are dependent upon labeled data, who's labeling it? There are products out there that'll say, you train me, right? You just come in every day, I'm going to give you 100 things, and you go like, don't like, don't like. And at the end of the day, you have your training set. That's your label training set. On the other hand, we've heard of plenty of examples today in the malware space where you can go to places. I always say we have friends and family. Don't ask what kind of friends, what kind of family, but we can get piles of bad stuff, and we can put them in one pile, and we can take normal stuff, and then we can kind of compare them. So that's pretty easy. But always be aware, if you are dealing with a classification product, are you training it, or is your vendor training it for you in terms of what you're buying? Algorithms, these things become kind of more computationally intensive as we go. Naive Bayes, nice, simple. The way I kind of like to describe this is, imagine in your mind's eye a 17-dimensional asteroid. Because 16 is easy, so I'm trying to break your minds at 17. But then imagine trying to describe the shape of this asteroid. And maybe in something like Naive Bayes, you just can basically describe it in terms of flat surfaces in one dimension, right? So you basically put it in a box, right? But that box isn't perfect, right? It contains maybe not all the asteroid, a little bit of the asteroid sticks out, a little bit of things that are inside the box are not actually in the asteroid, so the box does not fully approximate the shape. As you get more sophisticated in these algorithms, generally it comes at computational cost, but it comes at the ability to kind of curve those surfaces and fit them more like a glove to the shape of the asteroid, where the asteroid is the bad thing and space is the good thing in this metaphor. So Naive Bayes, we've talked about random forest and ensemble learning that you can do, a variety of techniques there. You see folks basically, oftentimes cybersecurity, particularly of the type that we're talking about, where an attack takes time, becomes really a time series problem. It's not at this moment in time, can we freeze the frame and without a notion of what came before and without a notion of what follows, can we declare it good or evil? So things like recursive Bayesian estimation and things like deep learning and neural nets can be used to do that. So particularly if you have things like recurrent neural nets which maintain some amount of memory. It's almost like, okay, you cook them a meal and they remember exactly what they had in the appetizer while you're giving them the entree, and so they judge the entree in relation to the appetizer. K-means clustering, again, is the most common technique around kind of anomaly detection and just clustering things in space. So lots of different algorithms. Again, the foundational approaches still applied across all of these. You can use neural nets for supervised learning / classification, as well as for anomaly detection. So these things are not in the same plane. Now, if you think about attackers, when they look at us, right, they think about, okay, I know you're using AI, let me screw with you. So what ways are they going to screw with us? There's a big pile of malware in a thing called VirusTotal that used to kind of be standalone, and Google owns it at this point. So this is an aggregation of, every bad thing. Well, not every bad thing, the most common bad things, let's put it that way. You won't necessarily find the most advanced nation-state pieces of malware that are used once for one target, but you'll find the most common stuff out there. So attackers know this. So what are they going to do? They basically pollute malware archives with legitimate samples. Let me put some stuff out there and pretend that it is malware, even though it's legit. Or maybe let me put malware out there, but put within it techniques that kind of mimic legitimate software. And then they can also, there's this whole gray area, PUPs as they're called, potentially unwanted programs, adware, other kinds of things that you will install willingly, rather than malware in the classic sense, which is something that might go after a particular vulnerability you have and an exploit against it. So you install this PUP, and guess what? So in these areas, you might want to expose techniques so that when those techniques are found in your malware, they're just confused for a PUP. It's just probably just a piece of adware rather than something that could be lethal to you. So that's one thing you see. For IP domain reputation system, this is like the hardest thing. Like at any given moment, depending on who you get a list from, half the internet is bad. And so, the question then becomes, well, what does that mean and how fleetingly is it bad? How much churn is in these lists? Something may not in fact be compromised, but just used as an intermediary, as a bounce point, and as a result, it'll end up on these lists, and then it'll get back off of these lists. So what do you do here? You pollute by creating and distributing malware that communicates with legitimate destinations. In fact, if you ran a bunch of malware in a sandbox, and you made a histogram of the top destinations contacted out of all that malware, Google will be number one, right? Because most of the malware is like, okay, let me just try connecting to Google to see if I'm actually on the internet, right? So the fact that a piece of malware looks up Google does not mean, and that Google shows up very high on that list, obviously doesn't mean that Google is, a C2 channel. Although you can use Google as an intermediary for your C2 channel. I mean, there have been people who have constructed C2 channels out of Gmail, out of Google Analytics, right? Anything that's kind of somewhat of a pass-through service can be utilized in that way. The other thing that we've seen attackers try to do is basically, overwhelm existing ML. So if you have, say, an anomaly detection workflow, if you're an AV company and you're going to basically, what you're going to do is you're going to do an anomaly detector against every piece of new software that you get a hold of, and when a new cluster appears, you're going to have manually a security analyst come along and basically look at it and label it. Well, okay, great. I'm going to create 10,000 of those for you in the next 24 hours, right? So I can basically, knowing kind of what your work process is, I can begin to try and overwhelm you just by, again, in VirusTotal, going through a series of proxies, just uploading a bunch of stuff and claiming it's malware. It's as simple as that. So there's also the problem of local data pollution. Okay, so there is this in vogue thing. If you go into large enterprises now, we're gonna have a data lake. I'm waiting for the data ocean to come next, right? But right now we're at the data lake level. What does that mean? We're just going to collect all the data we have in this enterprise. We're going to dump it all in, and then we're going to squint at it and see if we can see Waldo in it. I'm only being half facetious. Oftentimes, these lakes come into being without clear use cases that they're going to solve, which is generally a recipe for disaster. So the quantum of data in these lakes, I mean, you're talking, petabytes of data. You're talking about hundreds of gigabytes a day of churn going into the lake and then dropping out of the lake on the back end in terms of old data. It's rather difficult for a security vendor who does this for a living to ensure that there's data integrity. You can imagine inside of an enterprise where they have one data engineer whose job it is to kind of maintain this lake. It can be a difficult thing to ensure integrity there. So attackers can do two different things. They can either try large-scale pollution. So it's like, I'm going to screw with this lake to a point where you're not going to trust it anymore. So it pretty much, you're going to throw up your hands and say, this thing doesn't do the right thing. And what we'll see, for instance, is attackers will just do, we were just talking about device authentication. Attackers will just do some spoofing of IP addresses and just send stuff, which will get rebuffed, but create just these flares, right? And unless you have kind of sensors at layer 2 within your network, you're not even going to know where the hell they came from, what switch port. So you're just going to start seeing traffic from a whole bunch of IP addresses, even though it's just basically 1 or 2 compromised machines. They're all really coming out of the same port on the switch. But most customers have no means of actually being able to isolate that. The other thing you'll see is, where they look at that lake and they go, okay, now I know kind of the envelope for how Oliver behaves. Let me try and nudge some other envelopes over a little bit if I'm really patient, and this is more your long-haul nation-state attack. If I'm patient, I can kind of nudge things to a point where the thing I want to do will now fall within the normal envelope. So, the other thing that you tend to see is, am I attacking an active system or am I attacking a passive system? I mean, think about, AV blocking software. I'm attacking basically an active system. I give it an impetus, it'll immediately make a decision, good or evil. And it will block or it will allow. And so, in general, if you're role-playing against an active system like that, you can much more quickly find a hole because you're getting feedback immediately. In general, on the other hand, if you're kind of in a network where you're dealing with passive systems, you're doing these things. I mean, think about being inside of a bank vault in the middle of a heist, and you don't really know if some alarm is going off 5 miles away every time you make a move. You have to kind of move slowly. You may be moving more slowly than you need to. In other scenarios, things that you didn't think were going to set off alarms will set off alarms. So generally, if the systems that you're deploying are passive and they're kind of cumulative, they're harder, and this is quite frankly also where they're black box-ish, they're a little bit harder to exactly figure out what state is building up in this system and what pushes it over the edge. So you've got to think about also, when you create systems that are super explainable and interpretable, they also are generally pretty easy to countermand for an attacker who has knowledge of the blueprints of the system. And I don't mean blueprints in the sense of, the software, having reverse engineered the software, but blueprints in terms of how the system actually behaves. So things to take into consideration. Again, there's no free lunch. The other interesting things that we sometimes see on the data side is that, the data quality issue. So you start basically by saying, okay, I'm going to build a threat feed, and I'm going to buy a threat feed from 10 other companies, and then I'm going to integrate those 10 threat feeds into the one threat feed that will rule them all, right? In fact, we see so many of the threat intelligence and threat feed businesses built really around this fundamental principle. It's like somehow the secret sauce by which I combine these other streams of info will be great. Now, you'll pretty much, if you're in that business, you kind of say, well, if 3 of my threat feeds agree that this is bad, let's say an IP or a domain, then I'm going to declare it as bad. Great. Unbeknownst to you now, you get something where 9 out of your 10 threat feeds tell you it's bad, but what you actually don't know is that those guys are buying from the same source up above. And so, pollution of one thing splits out into 9 things. You're consuming it. It looks like 9 different, companies have come to this same conclusion. Effectively, it was just one data source, right? It just got obfuscated through the supply chain. So, knowing this, attackers will basically try and find data sources that are utilized by almost everyone. And these are oftentimes data sources, the reason they're utilized by everyone is they're cheap. Right? So there's an economic incentive model here. And they're cheap because they don't have a lot of process around pollution, keeping bad data from going in. So it's like the perfect storm. You go into a company that doesn't have great controls, you pollute their data. Because they're cheap, they're utilized by a whole bunch of downstream people, and those people basically then give you your great thing. And now, basically, the attacker has either created a large number of FPs in an area, or basically created a blind spot for you in a different area, something of his or her choosing. So, The other pieces are really thinking then about, how will attackers use ML? So up to now, I've kind of talked about, okay, if attackers know that you're using machine learning, what might they do to make your life harder? But now here's the converse. What if they use machine learning? And people will often say to me, well, there's never been an attacker that's used ML, right? But it's like, right, but the majority of ML that we have in the industry today is used offline. Let's be clear, right? We train up an algorithm and then it arrives kind of fully formed. There's nothing that makes it distinguishable as to whether that algorithm was hand-coded by a programmer writing if-then-else logic or whether it was trained using ML. If an attacker uses machine learning, and there are plenty of papers, there's plenty of experimental stuff out there for finding vulnerabilities, as an example, mechanizing the process of finding vulnerabilities in a piece of software. I can use machine learning for that, and the end effect of that is simply that I have more vulnerabilities and I have them quicker. It's not discernible on the defensive side whether that vulnerability was basically found using ML or whether it was found the old-fashioned way by somebody reversing. So that's basically another thing that you kind of have to worry about. And the other thing that was discussed earlier, right? I mean, given access to a security product, you can basically mechanize the process of really finding where its blind spots are, right? So it requires an investment. It's basically an adversarial machine learning problem. You're basically saying, okay, you have a toy and I have a toy and my toy is going to find out how your toy works, right? Rather than spending all the time and effort and energy of reversing it and every time a new software release comes out, looking at the deltas in the patches and reversing those, I can just mechanize the process. So this is not necessarily Skynet, right? This is not, oh, we've taken some active defensive scheme and we've handed it the keys to the kingdom and it's basically going to annihilate the human race. But AI and machine learning to a large degree is a means of automating things that we do manually today. And all of those offline things can be done already today. So the final slide, issues to consider. So if you're purchasing the end result of other people's ML, right? So you're going to go out and you're going to buy this product. It's the best machine learning product in the world. Ask them about the data that they use. Where does it come from? How actively do they operate on it? And how do they ensure it's not compromised? If, on the other hand, you're a company and you have the hubris of kind of doing this on your own, the number of times I hear in companies, it's like, oh, we got one data scientist on a data lake. And it's like, okay, good luck with that. How good is your ML team? Be realistic. I know you like them. I know you know their wives and their kids, but at the end of the day, it's like, do you have both statistical guys and Bayesian guys? Do you have a mix of different backgrounds? And where's your data coming from? Do you have the ability to kind of keep it from being polluted? And does it even include the right features? I mean, does it include the right variables? Because yeah, you may have all this data, 98% of it may in fact be useless for the use case that you have in mind. And at the end of the day, once you've done all the ML, whether you've bought a product or whether you've built it yourself, how much is left for your incident responders? Is it interpretable? Is it actionable? How much ambiguity is there in it? How much skill do they have to bring to bear? And that is basically the extent of my prepared remarks. Any questions?
Well, let's thank Oliver first before.
Mine is a quick one. Is there any work done using fuzzy clustering in this area?
We are not doing any, but I'm not aware, but I would be surprised if there is any technique in the machine learning corpus that is not being used by some company.
Okay, because in essence, if you're using C-means, you could have any one element belong to multiple sets to different extents. And you could probably...
Yeah, I mean, the trick is always defining kind of the scope and boundaries and the shape of the problem, and then picking a technique that most suits it and is least computationally intensive, because I think to a large degree, at the end of the day, we're still bound by how much compute we have and memory we have. So doing it as cheaply as possible to solve the problem at hand. Don't try and hammer in a screw, basically, would be my advice.
All right, thank you.
Hi.
Hi.
It seems to me that there's a little bit of hubris in attacking interpretability as a security measure because, in the event that your data is polluted, your models are being evaded, or, you've got some sort of adversarial learning thing going on, there's really, in a non-interpretable model, it's very hard to audit and figure out what's going on and make adjustments and things like that.
I mean, to be clear, I'm not attacking it. I think there are problems that are solved in the industry that are solved what I would describe as a non-interpretable way, but in a measurable way in terms of efficacy. A classic one for this is the black box that is fraud detection around your credit card usage, right? It's like, you will periodically get this call, and it's like, we rejected it. Why did you reject it? Can't really tell you. Quite frankly, they don't know, but they have proven basically that system on aggregate performs in a certain way. And so there are particular problems. For us, for instance, we do rat detection in a way that is just not going to be interpretable. It's taking a time series of data over a long period of time and trying to make judgments out of it. The interpretability of it would, you could expose it, but it would boggle the mind to try and get your heads wrapped around it. So there are classes of problems where I think interpretability is not achievable, or it's only achievable at the cost of efficacy. And then there are places where it is quite achievable to expose basically all of the underlying parameters, and it is understandable. But I was just commenting on neural nets as an example where it is just not going to basically be achievable in a complex neural net.
Anybody else? Okay, let's thank Oliver, and let's thank all the speakers of the session one more time. And we'll start back in about